Good morning. We have one more chapter on energy. So chapter 7 we went through and we looked at, we talked about energy, we talked about transferring energy. This chapter is going to focus on what we call conservation of energy. And it's a problem-solving technique. So let's go ahead and see what we're getting ourselves into here with chapter 8. First of all, we're going to talk about the forces, how energy is transferred through forces, and some forces are what we call conservative, and other forces are what we call non-conservative. So what this is saying is that work being done by a force on an object from one point to the other, if it's a conservative force, then that energy gets stored as potential energy. So the example they're using here is gravity. And we kind of saw this in chapter 7. But what we're going to say here is, there were those examples in chapter 7 where we took an object at a certain elevation and we lifted it to a higher elevation. Now, it wasn't always just from lower elevation to higher elevation vertically. If you remember, there were those examples of putting on my backpack and going from lower elevation to higher elevation. And what we found was the amount of work that required, it really just depended on the elevation change. It could be a very gradual rise to this higher elevation, it could be very steep, but there was a certain energy difference based on elevation alone. And so what we're going to do, and that's what this is showing here, is if we lift this object upwards, that's going to require work to bring the object to the higher elevation. And then if we lower this object back down, it actually turns out that we can get that energy back again. And that's how gravity works. Now, there are what are called non-conservative forces. Non-conservative forces, if we go in one direction with friction, energy gets converted into thermal energy along the way. So we lose what we call mechanical energy. If I now take friction and move the object back to the other side, I don't get the energy back again. Okay, so what happens with gravity is, on the way up, the force is downwards. On the way back down, the gravitational force is still downwards. So the force doesn't depend on what direction the path is. The force is set up in terms of different locations within space. Okay, so again, kind of a repeat here. They're introducing the idea of potential energy. Now, we used that phrase back in chapter 7, and what we said was, we talked about if we take an object and we lift it through a certain elevation, the work that we have to do in order to raise this object from a lower elevation to a higher elevation, it's given by the force times the distance. Now, if we're going to move this at constant velocity, which I think is kind of how we worked through these problems in chapter 7, the force then would be given, the force that we lift with, this external force or exerted by the hand, would have to be as large as mg in order to lift the object at a constant velocity. So that work then is the force times the distance, it's mgh. So what we can do now is we can introduce the idea of a potential energy. Now, the potential energy is the energy that's been stored when we've lifted that object, and that potential energy is also going to be given by mgh. So we can use that formula. We can have mgh representing the potential energy stored when we lift an object from a lower elevation to a higher elevation. So here's our textbook, right? And this is kind of our example of going from lower elevation to higher elevation. There's a certain amount of potential energy here there's less potential energy here. If I bring this up to this location, I could now drop this, and the potential energy would become kinetic energy. I could also attach this to some kind of a mechanical system and have the gravitational force on this pull something else up to that elevation. So once we've lifted an object through a gravitational field, that stores up a certain amount of energy, and that energy can be utilized to operate some machinery. We refer to this as mechanical energy that we have stored. And our formula is going to be mgh or mgy if we want to work in terms of that variable. So again, what we can do with this potential energy, we could drop the object. That would take the potential energy and convert it back into kinetic energy, which we introduced again last chapter. So the potential energy, this is kind of a good thing to realize. It's not that the book has potential energy. It's that there's potential energy in the interaction between the gravitational interaction between planet Earth and this book. Now, if we let go of the book, we drop it or something, we don't feel the Earth move that much. It's the book's motion that we notice. So we often refer to this as saying the book has a certain amount of potential energy. But strictly speaking, potential energy is in the interaction between two objects. So that's something to keep track of. Now, if we have gravitational potential energy as mgh or mgy, where do we measure that from? So I guess the question then is, when the book's on the table, is that zero potential energy? And then as we raise it, the potential energy becomes positive? And that approach works. We could define table level as zero. But what we're stating here, what they're stating, is that we really could pick any location at all as being zero. Now, if we did use the table as zero potential energy, then every time we raise the book to a higher elevation, that would be positive mgh. What would happen, though, if we lowered the book below the table? Well, once we've defined that 0 point, then points below that would be negative potential energy. Points above would be positive potential energy. So potential energies can be defined to be negative or positive. We just have to make sure that as the object is lifted through the gravitational field, we're going from lower numbers, maybe they're negative, maybe they're positive, into higher numbers. Okay, so that approach works. And again, we're able to, at our convenience, define what location we want to consider to be the reference point, the point that would be at zero potential energy. All right, here's an example using a roller coaster. So this roller coaster, if we look at the profile of the different heights, the different elevations that the roller coaster is going to go through, what we see is it starts out at this elevation, we'll call this elevation 1 or height 1. It goes up to height 2, and then it drops down to height 3. Now, what they've given us are differences in height. So there's a 10 meter rise in going from point 1 to point 2. There's a 15 meter drop in going from point 1 down to point 3. Now what they're doing is they're calling this Y, and it says we have a roller coaster. It's 1,000 kilograms, so it's a pretty substantial roller coaster. Moves from point 1 to point 2 and then point 3. And they're asking, what are the gravitational potential energies at the different locations? Now, they specifically say, what's the potential energy at 2 and 3 relative to the potential energy at point 1? So if 1 becomes our reference, then what we want to do is take the elevation at point 1 to be 0 potential energy. That means that point 2 is going to be in the positive region. We'll represent that as being positive. and point 3 will be in a negative region. So let's take a look and see how this works. And all we really need for this is our formula that we've derived showing that the gravitational potential energy is mgh, and that it just depends on elevations. So let's write down what the elevations would be at these different locations. They told us to use the first location, point 1, as a reference of zero potential energy. So I'm going to ignore these numbers right now. We'll come back to these. But right now I'm going to say H1 is at 0 meters. That means H2 is at 10 meters, and H3 is at minus 15 meters. And then I just plug into this formula. That says that at point 1 we have 0 joules of potential energy by definition. And then at point 2 I can put in the numbers m, g, h. Here's the gravitational field of the Earth near the surface, 9.80 newtons per kilogram. And that gives us potential energy of 98,000. And then when we drop all the way down to elevation 3, we put in the minus 15, and that gives us minus 147,000 joules. So that's just calculating how much potential energy, gravitational potential energy, at each location. Now, let me check quickly and see what is the difference in potential energy. On part B, what's the difference in potential energy when we go from point 2 to point 3? And so in part B, what we want to do is find out what's the difference in potential energy if we go from point 2 to point 3. So I'm going to write this as delta U. In some sense, all these potential energies are delta potential energies because, again, we get to decide where the 0 point, where the reference point will be for calculating our potential energies, and then all the potential energies are measured relative to that point. So here what we're going to do is this is our final potential energy minus the initial potential energy. Now this works out to be, if I take U3 and subtract off U2, we see that that's a drop of 245,000 joules. I'm going to start using kilojoules here so I don't have to carry around all these zeros. But that's going to be a potential energy drop of 245 kilojoules of energy. Now, what I have written up here, this is just kind of an aside, saying what if instead of this as our reference point, what if we had chosen point 3? Well, if point 3 was our reference, I would assign that the value of 0 meters for H3. H1 then would be at 15, and H2 would be at 25. We could take these numbers, define a set of potential energies for those 3 different levels. They'd be different, but the differences would work out to be the same. So it's only the differences, at the end of the day, it's only the differences in potential energy that will show up in our calculations. All right, we can also store potential energy in a spring. We've looked at ideal springs. Again, that was chapter 7. And we talked about springs having a natural length and setting this up as x equals 0. And then if we compress the spring or extend it, stretch it out, we can store energy. Now, when we looked at the springs, we saw that we could represent the force required to compress the spring or to be kx. And we put a minus sign in there when we needed it in order to show that the force was in the opposite direction of displacement. But and then what we also had done is we had calculated how much work is needed to compress a spring. Now, when we looked at this in chapter 7, we talked about this as the amount of work that we would have to do in order to compress the spring. And then we said when that energy transfer takes place, the spring ends up with a potential energy. So we can just use the same formula derived from chapter 7 and say that the potential energy stored in an ideal spring comes from integrating the force here, but it works out to be 1/2 kx squared. So, and we're pretty much going to stay with ideal springs. Take a look at the homework problems. There's a lot of examples there, I think, that you can look at. So, so what we've got now is we've got gravitational potential energy. We've got spring potential energy, so an elastic potential energy stored in a spring. What we're going to combine with this is the idea of total mechanical energy. So what the big E, the total mechanical energy, includes is it includes all of the potential energies in a system, in an object or in a system of objects, as well as all of the kinetic energies. So if we go back and think about the roller coaster, right? If we start with the roller coaster with a bunch of potential energy, as the roller coaster drops, that potential energy is converted to kinetic energy. And so what this is saying is, if the forces we're dealing with are conservative, now that would be gravity, that would be the forces in a spring, in an ideal spring, then we can define a total mechanical energy as the kinetic plus potential. And conservation says this, it says that if we look at before and after, that mechanical energy will be conserved. We'll look at some examples, I think that will help. So if the forces acting in a system are only conservative forces, then the mechanical energy will be conserved. All right, so here's an example we can start looking at. So let's say that we have, wow, that's a really big rock. So this person has this object lifted up. Maybe it's a textbook, maybe it's a rock. It looks more like more like a rock than a textbook. But this person's gonna, and look, they even went on a stool so they could get a little extra height here. So we're gonna say that we're gonna start off at some height, right, h, and then we're gonna let this thing drop down to the floor. Now, they've defined the y value to be 0 at the floor, and they've defined it to be h at the top. So what they're saying is at this point, all the energy is potential. The object is not moving, so there's no kinetic energy when it's at rest. And then what happens is it drops and it picks up speed. And so halfway down, half of the potential energy would be already converted into kinetic energy. So we start out with the energy being 100% potential. Halfway down, half of the energy remains potential, half has been converted to kinetic. And then by the time, just before we hit the floor, the potential energy is gone, and all of the energy is kinetic. Now you may ask what happens when it hits the floor. Contact with the floor is not a conservative force. And so at that point, all the energy that we had stored up becomes thermal energy. The floor is a little warmer, the atoms and molecules have a little more vibrational and rotational energy as a result of that impact. So the conservative, the energy conservation part of this problem, mechanical energy conservation, works as long as the forces are just the gravitational forces. Right up until contact, this is going to work fine. So at every location along here, the total mechanical energy can be determined by taking the kinetic energy at that point and adding it to potential. So if I take 1/2 mv squared plus mgy, or mgh, at each location, that number remains a constant. So let's say that we start off with 5,000 joules of potential energy. By the time we're halfway down, that potential energy is at 2,500. Now, there's 2,500 joules of potential energy no longer there, but the 2,500 joules of potential energy have become kinetic. And then by the time we get to the bottom, the 5,000 joules is entirely kinetic. So here's an example they're asking us now. They're saying that what we're going to do is start at the 3 meter mark So yeah, that's a pretty good stool there. So we're going to stay up here at 3 meters. I need to stand on a stool and drop this rock and calculate the speed once it has fallen to the 1 meter mark above the ground. So I guess what we're doing is starting at 3 meters and letting this drop to 1 meter and seeing how fast it's going. All right, here's what it looks like. Now I tend to, on these problems, use point A, point B, point C. So at point A, we're at a height of 3 meters. And then at some later time, we've dropped this rock. We're down to 1 meter. And then I added in point C. I don't think they use this. I think that's just something I added. Yeah. So I added point C where H is equal to 0 meters. Now they told us that the mass of the rock is 5 kilograms. Right? No. Okay, I added that in, right. So they're showing that regardless of what the mass is, we can calculate how fast it's traveling. I wanted to put the mass in just so we could practice looking at how some of these formulas work. So I'm going to say, this rock is it's 5 kilograms. So we'll say this. We'll say that the total mechanical energy at each of these points is equal, and that's because the only force at work here is gravity, and gravity is a conservative force. So a little later we'll get into friction and air resistance and mechanical energy losses, but for now we're assuming, again, it's kind of like dropping this on the moon with no atmosphere and assuming that all the energy stays within the system. So at each point, I can take the kinetic and the potential, and I can set those equal. So the combination of kinetic and potential that we start with stays fixed through the problem. So let's see how much energy we do start with. So I started with potential energy at point A. Now at point A, the potential energy given by mgh works out to be 147 joules. So that's how much potential energy we're going to start with, and that says when we start off at point A, well there is no kinetic energy, right, because it's at rest, so no kinetic energy, 147 joules of potential energy, that means a total of 147. So that's the energy we have to work with. Now the kinetic energy that we end up with at point B, and that's what they're asking us about, that's at a height of 1 meter. And from the formula here, what I can see is kinetic energy at A, well that was 0. So the kinetic energy at B is going to be given by UA minus UB. So at point B, the potential energy will have dropped to 49 joules. We started with 147, now we're all the way down to 49 joules, and that says that the kinetic energy that we end up with will be 98 joules. So that's going to be 98 joules of kinetic energy. 2/3 of the energy is now kinetic. I can take my kinetic energy formula, which was 1/2 mv squared, and I can solve for v from 2k over m square root. I put all those numbers in, I put in the 98 joules, and it says at point B, the rock will be traveling at 4.43 meters per second. All right? Now, if we trace this all the way through, what we find is that the mass, there's a mass term, I think we can see it here most easily, maybe. Yeah, so what we can see here is that the kinetic energy is proportional to mass, the potential energy is proportional to mass, so when we set these formulas up with kinetic and gravitational potential energy, the masses will cancel out. So we really did not need necessarily to know the mass. We could have just done the algebra and had the mass cancel out. Here's another example. let's take a look at this roller coaster car and use energy conservation for this. So it's assuming the height of the hill, this is at 40 meters. So that's a pretty good sized roller coaster, you know, it's 120 feet more, 130 whatever feet in the air. And the roller coaster starts from rest. So I guess the roller coaster has been pulled up to this location and then given a very gentle push over the edge. So we're treating that as starting off at rest. And they want to know how fast the roller coaster would be traveling here. So point A, point B, I'm not sure if we need this. Do they ask about it? Oh, at what height will it have half the speed? So, and they're saying to take y equals 0 or h equals 0 at the bottom of that hill. So let's take a look. Here is point A. Here is point B at the bottom. The height here, the difference in elevations. The height here is 40 meters. The height at the bottom is 0. The velocity at the top is 0. So the zeros are good, right? Wherever there's a 0, the potential energy term or the kinetic energy term will drop out. And that simplifies things. So at point A, we have no kinetic energy, so that goes away. All we have is potential. At point B, we don't have any potential energy, we only have kinetic. So we can take mgh at the starting point and set that equal to 1/2 mv squared at the bottom. So make sure you're keeping track of locations. But in this case, I think it's simple enough that the velocity corresponds to point B, and the h corresponds to point A. Now, as we talked about, the masses here cancel out, so I don't really need to know that the roller coaster is 1,000 kilograms or whatever. I can solve this for v squared is equal to 2gh, and taking a square root, the velocity then is 2gh square root, and then I can put the numbers in. Now, for the velocity calculation, I went back and put the gravitational field in terms of meters per second squared to make the unit conversions more simple. And I got meter squared divided by second squared. I take a square root. It's going to come out in meters per second. So it says that the speed at the bottom is 28 meters per second along the track. So this is one of the nice features of energy conservation. Notice that as long as we drop from one elevation to another elevation, and we can ignore friction and air resistance, if those forces are negligible, then it doesn't really matter how steep this track was or what the curve of the track looks like. It just depends on starting and ending elevations. Those are the things that I have to know. Now, for part B in the problem, they said let's find the height at which the speed is 1/2. Let me go back and see if I've carefully read the problem. At what height will it have half this speed? I think I did it. I think I did it the other way around. I think I did not carefully read the problem. They want me to solve for a height, but I did the problem wrong. So anyway, I guess we go ahead and solve it the way I've solved it. What I read, and I didn't read it very carefully, was that we wanted an intermediate height, h1, that would be half of h2. So I did a ratio and said that the velocities at different heights would be given by this. Now, what I could do is this. What they said, if I go back and read it carefully now, at what height will it have half the speed? So the speed is half. All right, so I could say that V2 is 1/2 of V1, or this would give me a factor of 4 because it's squared. And that would say that the height then would be where h1 would be 1/4 of the height. In any case, I solved it kind of backwards. I assumed that the heights, 40 meters and 20 meters, so I solved for how fast is it going when it's dropped halfway. Now when it's dropped halfway, it's already going 19.8 meters per second. So, all right, apologize for that. Here's a good, here's kind of an interesting conceptual problem that we can take a look at. What we've got is we've got two water sliders, and the question is, well, if they both start at the top and there's no friction, no air resistance, then by the time they get to the bottom, they'll be traveling at the same speed. But how much time does it take to get to the bottom? Are they going to end up taking the same amount of time? Now, notice that when we use these potential energies and kinetic energies, the potential energies are in terms of distances, in terms of heights. They don't tell us how long the process takes. So we can use energy conservation to calculate how long a process takes, but it's more involved. It's not very straightforward. So notice that we don't have detailed calculations of how much time these processes are taking. But in this example, what we can do is this. We can say that if we look at these two people sliding down the slide, Paul here starts out going really slow and then picks up a lot of speed at the end. Kathleen, on the other hand, begins to go fast right away. Now, that means that Kathleen is going to be traveling at a higher speed than Paul at different points along the drop. Kathleen's going to get to the bottom first, right? But again, once they get to the bottom, they'll both have the same speed. Eventually, Paul's going to end up with the very same speed that Kathleen has at the bottom. It's just going to take longer. All right, here are some recommendations of how to solve problems. We've been, in chapters 4 and 5, we've looked at forces and accelerations. So using forces and accelerations, we were able to go in and solve a lot of different problems. We were able to solve how fast objects were traveling at different locations. Now, with chapters 7 and 8, we now have a different approach. Using work and energy is based on the very same principles as when we were using forces and accelerations. When we introduced energy and energy transfer, that was in terms of forces. We kind of went through the details of how those formulas are derived. But now we've got this choice between using forces and accelerations or using energy conservation. So this says that when we can, the force approach works well if we have forces that are well defined at all locations. So for example, let's go back and look at this. If in this problem, all we're trying to find is just how fast are they traveling at the bottom, energy conservation is going to be much, much faster. It's going to be a preferred way to solve the problem. Because in order to calculate the forces and the accelerations at every point, I would have to have information about the angle that the track is tipped at every location. I would need to know, moment by moment, what is the angle and what's the acceleration. It would be a really complicated calculus problem to go back through and add all those effects together. Whereas energy conservation says, look, all we really need to know is starting point, ending point, and we need to know that the mechanical energy was conserved between those points. If we know that, we can solve many problems very rapidly. Now, it's not going to solve, it's not going to easily solve how much time it took to drop, but it will tell us how fast the objects are traveling at the bottom. So let's do this. Let's bring in springs. So we had also looked at springs and how the energy is stored there. So what we have here is we have this dart gun where we push a projectile into this device and we store up energy in a spring. So what's going to happen is, to start with, we have the spring is compressed, the dart is at rest. So since the dart's at rest, we can ignore the kinetic energy that we start with. All of the energy we start with is potential, and it's stored in the spring. And the formula we derived for this was 1/2 kx squared. Now, after we fire the dart, notice that there is no energy stored in the spring. There's no energy anymore there. The dart is moving, and what we're assuming here, and maybe it's a good assumption, maybe it's not, that all of the energy has been efficiently transferred from potential energy in the spring into kinetic energy of the dart. Now that's the assumption we're making. Anybody who's played around with dart guns probably realizes that there's going to be some energy loss due to friction, whatever. But as you know, as maybe a reasonable approximation, we're going from total mechanical energy is entirely 1/2 kx squared at this point, and then in picture B, it's 1/2 mv squared. So let's see how this works. Here is the energy stored in the spring at time A, and here is time B, and now all the energy is kinetic. So we'll say the total mechanical energy at point A matches the total mechanical energy at point B. That says we can do potential plus kinetic at A equals potential plus kinetic at B. We can substitute in all of the formulas for spring potential energy and kinetic energy. And then we'll say VA is equal to 0, XB is equal to 0. So that means two of the terms drop out, and we've simplified down to 1/2 kx squared is equal to 1/2 mv squared. And I can solve that for V. So the V squared here is given by K over M x squared. Now, these are numbers that were given. I hope I read the problem carefully. So the K value is given, and the compression distance is given. This was the K value for the spring. This was the mass of the dart. And this is the distance that the dart was compressed. When I put all those numbers in, I end up with a speed of 3 meters per second. So there you go. There's another example of, I don't have to do the details at each step of how this spring exerted a force back on the object. What we do is we do kind of a one-time calculation. So we did that for the gravitational field. We did a one-time calculation saying potential energy is mgh. For the spring, we did a one-time calculation of potential energy is 1/2 kx squared. And then the integration is done, and we don't have to redo that every time we come up with a problem like this. So I don't have to go back and reintegrate those formulas. I can work from the formulas that we've already derived for the potential energies and for the kinetic energies. All right, now in this example, what we've got is we've got an object that starts out at some elevation. So I'm going to say this is picture A. So there's a series of pictures A, B, C. We start off with an object at some elevation H, and that's 55 centimeters. And the mass of the object is 2.60. Quickly, let me go back to this example once. Okay, if I look at the spring potential energy, it doesn't depend on the mass. So the masses will not cancel out anymore. Remember back when we were doing gravitational potential energy, the masses would all cancel out. But in this case, once I'm bringing springs into this, the masses won't cancel out. We're going to have to know what the masses are. Just a clarification there. So I am going to need to know that this is 2.60 kilograms. We're going to drop this, and picture B, this is a good place to stop and ask what kind of energy do we have. Well, in picture A, it was totally gravitational potential energy. There's no kinetic energy, the spring is not compressed. The spring is still not compressed in picture B. All of the gravitational potential energy is now kinetic. Now, notice what happens when the mass compresses the spring. This is the most complicated step because, let's see, I had kinetic energy here. Once I reach the very bottom and it slows down and stops, I no longer have kinetic energy. So the kinetic energy is gone. Now, there's two different types of potential energy here. There's clearly potential energy stored in the spring. There's also a drop in gravitational potential energy. So let's take a look at this and look at all the numbers and keep track of the potential energy. So what we'll do is we'll say that the potential energy that we start with, let's see, this was picture A, this is picture B, picture C. It turns out in the problem, they don't ask us, I don't think, determine the spring constant, K. So we're trying to calculate K here, is what we're being asked to do. Now, I don't need to use picture B. I drew it, I showed what was going on, but I really can work in terms of picture A and picture C. And so let's do that. Picture A, time A, has an H value of, oh, I gotta go back and look at this. Oh, there it is. So there's a 55 centimeter drop here. And then the spring compresses by 15 centimeters. Now I went back and used X for that additional 15 centimeters. So what we could do is we could say this. There's a gravitational potential energy in the first picture, mgh. There is a gravitational potential energy here, mgh, plus there is energy stored in the spring. So I can say mgh that we start with. Now, I decided to call this the 0 point for gravitational potential energy. And so I'm down below my 0 point by an amount minus mgx, where x is treated as a positive number. I've got the minus sign out there where I can see it. And then there's energy stored in the spring. Now, what this tells me then is if I'm trying to solve for k here, I can take this term, that's the potential energy stored in the spring, and set that equal to mgh, I'll bring this term over, plus mgx. What that works out to be is mgh plus x. So notice my calculations depend on the total amount of drop between point A and point C. The calculations are going to depend on h plus x. They don't really depend on where I picked my 0 point. So the 0 point, I could have picked this as the 0 point, I could have picked this as the 0 point, or here for the gravitational potential energy, because at the end of the day, I'm just going to be taking differences anyway. So the h plus x combined, that total 70, it gives us a total 70 centimeter drop. So here is the m, here's the Earth's gravitational field. When I calculate that, I get 17.8 joules of potential energy that will be stored in the spring. In picture C, at time C, right here, I have 17.84 joules of energy stored in that spring. Now to calculate K, what I can do is I can take, well, this formula here, and just, let's see, I multiply it by 2, I divide through by x squared, and that's what I've done. So I multiplied by 2, divided through by x squared, and what it's telling me is that the K value, the stiffness of this spring, would be 72.8 newtons per meter. So there's the K value, that's what they asked us to solve for. It looks like we were able to determine that number. Now, we made kind of a big deal that we did need to know the mass in this case, and let's ask and see why that is. If this thing were 10 times the mass, that would lead to a bigger compression of the spring, right? So the m's don't cancel out. Having more mass here does not affect the velocity at this point, but it does affect how much the spring will compress. So I needed to know m in order to solve the problem. Ooh, here's kind of an interesting, here's an interesting example that we have here. Let's take a look at this. What we've got here is a swinging pendulum. Now, we've got a lab on this, right? Looking at measuring gravitational fields using a swinging pendulum, and many of the same force diagrams that apply to this apply to the swinging pendulum lab that we have done. Here is this pendulum swinging back and forth, and it says that we've got, it's a simple pendulum, meaning that we have a string with negligible mass. All the mass we're going to treat as being concentrated in one object, in the pendulum bob at the bottom. And the length of that's going to be L. The bob is being released, so we're going to take this and we're just going to let go. So we let go of this part of it, and it's going to swing back and forth. There's going to be a gravitational force accelerating this object back towards this location at the bottom. So what they're saying is part A, describe the motion of the pendulum bob in terms of kinetic and potential energy, and then determine the speed of the bob as a function of position as it swings back and forth. Find the tension in the cord. So a lot of stuff they want us to do here. Let's go ahead and get started. So if a pendulum's swinging back and forth, that's different elevations, and that's going to be different gravitational potential energies. Now, for something that is swinging back, for something that's going around in a circular path, if you think of a pendulum, the path that it follows, it actually goes back and forth along a circle. So it doesn't complete a circle all the way around, although I guess it could. But for a pendulum just oscillating back and forth, it's following a circular path. That means that what we could do then is find I'm going to set the gravitational potential energy to be 0, my 0 point, my reference, at the center of the circle. That turns out to be, mathematically, it saves you a few steps. So it's the simpler way to approach this. You might think, well, why aren't we defining at the bottom? And it turns out that you need a couple more terms to work from. So if we define the potential energy to be 0 at this location, then all these locations below this are going to be negative potential energies. But we've seen negative potential energies before, and it's fine. It works. So for the potential energy then, at each location, we're going to write this as mgh, where, okay, I guess here, potential energy of gravity minus mgh. So I'm putting that minus sign right where I can see it. And h is just going to be measuring a distance. Now, if I look at a pendulum located at some angle theta naught, then, or some angle theta, the distance that I drop down to get to that location is going to be given by L cosine theta. So H is equal to L cosine theta, and let's see if their diagram's any better than mine. maybe it is, maybe it's not. Yeah, I like it better. You didn't draw the best diagram on that. So here is L, and this is theta naught, and so this distance then would be L cosine theta naught. Now in general, when this thing swings back and forth at any location, the drop, the distance that we are below the reference is going to be given by L. So this is a cosine theta. This is a general formula for any location as the pendulum swings back and forth. So I'm going to use this as my formula, and let's check it out here. At the very bottom, when theta is equal to 0 degrees, the potential energy will be minus mgl. Yeah, that makes sense. So I think we've got this set up correctly. So let's start at point A and let this thing swing back and forth. So point A represents the starting point. Point B represents any other point along the way. Now, the potential energy then that we start with is mg minus mgl cosine theta naught. We're starting from rest. So that kinetic energy will be 0. At any other location where theta is just some random theta, we can write the potential energy again as minus mgl cosine theta. This was theta naught, our starting point, and this is some theta farther along. And then at that point we'll have, at any other point, there's the possibility of having some kinetic energy. So we'll say this is the kinetic energy. We'll add these two together and set them equal to these two. So the kinetic energy that we have at point B plus the potential energy, which we've listed, is equal to the potential energy that we started with. Now this is back to being a gravitational case. There's no spring here. All the m's did cancel out. So the m's drop out. We can multiply through by 2. And we end up with a formula that says that the speed as a function of position is equal to 2gl cosine theta minus cosine theta naught. Now that's v squared, so that would need to be square rooted. But that's the formula that we're ending up with for the speed as a function of theta. Now, in the later part of the problem, they ask us to go back and calculate tension. Now, that's kind of interesting to go back and calculate tension because so far in these chapters, in Chapter 8, we really haven't been looking at force diagrams at all. We've been doing everything in terms of kinetic and potential energies. But what we can do now is we can go back and show that, yeah, if I'm doing an energy calculation, I can go back and do a force diagram. So here is the force diagram acting on that pendulum bob. There's a tension in the string. Now the tension is going to line up with the direction of the string. And then the only other force is gravity. And it's going to be most convenient to divide gravity into sine theta and cosine theta components like we've done before. Now remember, this is a tricky step, so we've had practice doing this before, so we have to make sure that that box tips so that mg cosine theta lines right up with the tension. See, here's the angle designating where the pendulum is located, and if I follow that down, that theta there is the same as this theta down in my force diagram. So what's driving this system back to equilibrium is mg sine theta. All right, now how are we going to solve for tension? And in the radial direction, in the direction along the axis where, or the coordinate axis where tension is located, there is an acceleration taking place. You know, you may think, well, isn't t just equal to mg cosine theta? It's not. Okay, so we're going to have to take a closer look at the acceleration that's coming up. Let me take a quick look at the time too. It may be that we're coming up on taking a break. I think I'm going to do that. Let's go ahead and take a break right now. And we'll come back and we'll look at the second part of this example. So now's a good time. Okay, any questions, let me know.